And if you want to get more information, just send an email to us or to the main address of IABSE, and we will stay in contact with you. So this is the second webinar related to the study of bridges against fire, vis-a-vis fire hazards. And if you have any questions, you can just send them or write them in the questions and answers section of the Zoom, and then we will reply or answer all the questions at the end. Just let me remind you that IABSE organizes many interesting conferences and seminars. So the registration for the Ghent Congress is open, the early registration, and also that the abstract submission for Copenhagen, it is also open. So I hope that you will be able to join any of these events. And now I will briefly introduce the speaker of today, Stefan. So he's a distinguished structural engineer. He graduated with honors from the Warsaw University of Technology and has worked in Poland, also in Austria, and also in Canada. And he's currently working with CIMA Plus in Canada and is specialized in the design of bridges, tunnels, industrial structures, vis-a-vis fire hazards, and also in seismic retrofitting. And he's also the vice chair of our task group. So whenever you want, Stefan, we are ready. Thank you.
Thanks, Nacho, for this introduction. So let's start with our part 2 of the structural design of bridge against fire hazards. We met for first time in May. Now we're going to continue with the subject. So I will just go quickly. Was prepared by our task group focused on the importance of bridge fires and the reason for that, for sensitivity of bridges exposed to fires, dealing with hazards, and fire engineering related to these structures. So in the part 1, we presented examples of bridge fires and structure response to fire. After the introduction for the why, this aspect is very important, comparing for other force of nature considered in codes and standards. We're gonna talk about design for fire in this second part of presentation, risk analysis, and dealing with fire hazards, focusing on the protection concept, reducing risk of fire, and perhaps the most important, holistic approach to fire within the life cycle performance of bridge structures. So design for fire, we've used in North America NFPA 502 standard. NFPA stands for National Fire Protection Association, which is a very good example of how to approach the design of for fire for various structures. Start with tunnels, but bridges and other limited access highways are covered also by this standard. That's basically for the structure which are over 300 meters long, but some elements, I mean, and that's despite the fact that the land is mentioned in the standard for performance structure elements is considered and should be covered in to provide adequate level of resistance. The standard says that for engineering analysis should be prepared to be performed for the structures and to assess the risk, the level of risks. And of course, the aspect, and that's also, from the perspective of the tunnel being covered by this standard, this safety of people to be included in this analysis. In case of bridges, of course, it's less important than in tunnels, but anyway, it's a factor we should take care of. In this engineering analysis, the standards show different aspects that should be considered. And bridges, I want to underline it, not different from tunnels from this perspective. You can find also in this standards reference to other a publication which can help in this this exercise. So let's talk about risk analysis of for bridges. The first category, first family is related to risks of fire. So in case of roads, and we should make a difference between the fire under the bridge or above the bridge, on the bridge. What's important is AADT, annual average daily traffic, for number of tankers, dangerous goods included, in passengers included in this data, and means of firefighting is possible or not. I use to put some examples of the fire we presented in the first webinar. I mean, the first part of our webinar. This is the fire of the in the Montebello, California, as you recall. Railways. This is very important. Transportation dangerous goods is an important aspect of this family. Condition of railways, condition of rolling stock, and speed operation of trains are part of consideration. I use here a picture not related necessarily to bridges, but we went to very, very painful experience in Quebec in 2013, where major accident took place with the derailment 74 cargo of train, and loss of lives, very important loss of lives. So that show important of combustible load those trains could present for bridges. Waterways, risk of transported cargo, ships, especially after collision. So we have an example from 1973, where two ships collided in New York, and passing the Verrazzano Narrows Bridge. We're very, very close to the bottom of the River Scotch, but no problem. Parking storage under bridges. We had examples show below from the Matilda Bridge in France, and the main bridge in Warsaw, where storage material was cars parking, trucks parked in France, or wooden decks stored in Warsaw, representing important combustible load, and so risk on catching fire, even considered voluntary action, should be covered. Firefighting is another element we should keep in mind. So another aspect is another family of elements is parameters reflecting performance of bridge fires. So combustible load design fire is on the one side, location of fire is on the other side. Heat transfer propagation of fire in the structure itself is quite important, and structure response based on the type, concept, materials, etc., should be taken into consideration. Now, probably the most important aspect is the impact of such fires on the network, economical, social, other aspects. So that's from the perspective of the engineering analysis and the results. It is major elements we have to keep in mind. So now the question is any quantitative risk assessment appropriate for bridges? My answer is no. When you refer to the NFPA 502, engineering analysis is not quantitative. By the end of the process, we have still, stay with the question how to deal with the consequences. And I would like to refer to the word of tunnels. By the end of the century, it's like low probability and no important consideration for the risk. And after 5 major fires in Europe, with heavy losses of human life, so it's completely different approach to this risk, and still is no number attached to the potential risk and then the consequences. But we have to, somehow, look at it from the perspective, overall perspective of what can we have from the fire in case of the power, of the type of structure, and the general risk for breach under consideration. So we created in the task group and agreed to evaluate. I mean, in an impact we could expect from such fires. It's starting to be weak or even not defined to very heavy. It's on the left side of the table. We considered for the location of fire under the bridge, on the bridge. In the case of the fire on the bridge, we use two levels in the bridges, with two levels of traffic. What can represent for potential impact, and the type of structure on the left side, concrete, steel, slabs, beams, monolithic, etc., etc. And you can see, and in terms of power, which very, very important, very big is a vessel and cargo trains, tankers, heavy good vehicles and cars, with the power of over 1,000 megawatts to about 10 megawatts for cars, which is quite small. And the colors can help in the evaluation of potential we can have for any case and any structure in any, but not in terms of, for, as I said, before, that's in the overall perspective for the risk, for the consequences of the risk of fire. We tested this grid with the examples we presented to you in May. The first family was tankers, fuel under bridges leading to losses. We have these bridges we discuss in the first part of the webinar. The bridge in Alabama, Vitalbrücke bridge in Germany, bridge in Auckland, Arthur Mays for Detroit, etc., etc., etc. So those are, you can see here, with the fire load of tankers, with the impact of being heavy, moderate to heavy. And another family is vehicles or bridge storage under bridges. We had examples of viaduct in overpass in Germany, Matilda Bridge in Rouen, and the bridge in Warsaw. So they were in the this you can see this in the rectangles, and the expected impact was from the heavy, moderate to small. Vehicles and bridges, and quite a few examples for that, with a very, very low impact. So that's what we had in the presentation, the first part of the presentation. We use the examples we treated there. So what we can say that it anticipated losses had place in the reality: steel beams, collapse, or heavy damage or demolition, concrete bricks, heavy damage or demolition. And important conclusion also that fire of any material stored under the bridge can lead to important damages. So combustible load and fire scenario should be assessed. Now, dealing with fire hazard. Let's start with the first, we can perhaps have in mind is protection. We know of the examples of protection for high temperature are used industrial furnaces, where we use refractory linings, test cell for engines for testing, with the with the stainless steel plates and bolting. Tunnels, we have fire protection for quite daily application all over the world after the series of fires are referred to by the end of the century. We have buildings, as example, we have protection of steel elements sprayed or for boards. We have also paints, tumescent paints, with some limited performance. That's very important to keep in mind. It's not, the recipe for any kind of risk, and the performance is quite low. So in case of bridges, protection is very problematic. We prefer see structure exposure to for inspection. So it's hide the structure of any protection. For exposure to environmental attacks, it's not seen. Does present also additional weight and for traducing for wind and earthquake loads, especially in the case of existing bridges, where the problem of upgrading is quite important, and no protection for the important fire loss, like in case of trains or vessels. So in conclusion, it's not protection, but other means should be considered in case of bridges. Concept. There are cases we know where the fire performance, performance under fire is considered in the design to resist to high temperatures with some loss of covered rebar. So collapse is prevented, but those structures should be repaired after fire. But in a way that allows to keep somehow original concept of I'm referring here to concrete bridges, and consider the temperature losses, additional loss in the design, but those loads should be reflected in the analysis. This is very important to be underlined, because the expansion and the thermal gradient are important loads should be resisted by the system. We can think about increased height of bridges. It's relative. We have example from Germany, this Vittelbrücke, where the bridge was had to be repaired of the fire, even if the height was very, very important. And we can see it's very high. So as a solution for bridges, it's rather questionable. Reducing risk of fire probably the best approach to deal with fire hazards. So on the roads where the most important combustible loads are from tankers and heavy good vehicles, the mandatory use of first lane, it's good for solution. Reduction of speeds, crash walls, and consider also regulated and unregulated cargoes on the roads, which you see on the next page. This is quite well covered by the NFPA 502, by the way, with a series of elements to be considered, how to deal with this element of risk, where we have population density to be considered. We have I would go quickly, so the NFPA standards are really available, so you can see all this aspect treated in details. A type of highway in this analysis, quantity of hazardous material to be expected, emergency response for capabilities in the area, consultation with the public, for exposure, other for adjacent buildings and infrastructure to eventual risk is very, very important. If consideration for the terrain, how does it look like in terms of risk for the traffic? And the global network could be which could be affected by the eventual accident. Alternative routes as well, and to direct the traffic of vehicles at risk. And effects on commerce in terms of money could be involved by this element. I put here, bridge and risk. We can, there's many of them. So any type of intersection, any for 2 level, 3 levels construction represents risk, and all of that, I mean, should be addressed somehow if we can take off the fire as potential hazard in the analysis. So now I was referring to the roads. Now we are the railways. We mentioned before conditions on the tracks, rolling stone, and for control reduction of speed, very important. So what happened in Quebec was, no one of them was under control. Configuration protection of falls of crash was eventually, in some cases under the bridges. The waterways, it's the highest fire category, so it's not very frequent. It's quite, rare to see the risk, but should be somehow covered by the analysis, and especially in the case of particular ships or vessels, those after collision. So in case of bridges across rivers, that's part of the engineering analysis. Spaces under bridges, as we learn from example you presented in the first part, as Kurt represented, it could be important in terms of impact. So how to deal? You see here, the bad example on the left side and the good example on the right side. We have also in the cases where the spaces are used for the public use. Acceptance of risk. That's maybe the most important, very simple and cost-free solution. The risk is low. It could be further decreased by some means. So accepting should be based on the role of the bridge in the network and the impact, economic and social. Both of them should be considered, and make a difference between less important bridges and important bridges. Those are important bridges are already covered by NFPA 502 for 300 meters and longer, but should be extended to all bridges with some level of importance for the traffic, for the network. So design for fire, I mean, when we approach the design, I mean, it's very not quantitative, as I said before. So we have, take care of various elements, various, and we put them in the table here, and we see design fire for bridge, effects of fire, impact, environment, conceptual design, detailed verification, etc. Everything is should be included in this approach, and based on with some kind of decision mass. You tell me, that we refer to no numbers, but those numbers here will somehow guide us in the decision-making process. What kind of bridge, where to build, how to build, and what kind level of risk we can accept. Now, I've mentioned at the beginning, the last point was the holistic approach to fire, which should be included as part of lifecycle performance. So that's very important because the probability is very low of fire. And should this be always part of life cycle engineering concept? Life cycle engineering concept covers 100% of bridges through 100% of the life length of those structures. So they're designed for fire, which can have different type of impact. And once again, two examples from the presentation, from the previous presentation, May could be put in the perspective of how those elements perform in the during the life. So I'm sitting here in Montreal, in Canada, and the problem of corrosion is very important. So the example you can see here below, coming from my province, Quebec. So that's the primary element of design, not necessarily fire. And fire, in case of brazes, would more lead us to the concrete solution, not the steel, which is more sensitive, more vulnerable to this risk. And how to deal with this both aspect. We have already many examples of poor life cycle performance of the standard projects. So the fire risk should be always put in the perspective of the life cycle performance, because the probability is low. And I said before, it's dealing with the risk is perhaps the more important factor than the design. And the design, and we experience, always, the problems with performance of bridges and collapse at bridges. I have the pleasure to be a vice chair of the another task group of the IABSE, which is dedicated to the collapse of bridges. Many examples of the poor life cycle performance of those structures. So that shouldn't be forgotten. You should keep in mind. And once again, an example, it's deterioration of bridges in Quebec and the use of steel is not very much in line with dealing with fire hazard. So they probably will not prevail in most cases as far as design is concerned. But that's what try to sell here as a point is, life cycle performance is an overall aspect. Fire of bridges should fit in this concept. So let us, say that we mentioned at the beginning in the introduction that the risk of losses due to fire is 3 times higher than in case of earthquakes, and earthquakes are covered by standards. Fires are not. ECOTS. I mean, yes and no, but you tell me that an FPA is take care of, yeah, that's for sure, but not in terms of design. And issues are complicated, are quite complex. That's like in the world of tunnel. So there's not a general recipe. An engineering analysis is the tool we should use to define the consequences. I mean, the level of risk and the consequences we can live or we cannot live with in case of any breach under consideration. So reduction of risk in the case of existing bridges, it's we mentioned the avenues for solution and the level of road management is a reduction of risk, acceptance of losses in some cases, and some other specific aspects related to any structure. In case of new bridges, could be included the conceptual design on this to the same level. We mentioned the bridge with the loss of concrete cover of the rebar, and assessment of the risk related to so very, very high combustible loads represented by tankers of dangerous goods. Firefighting is another aspect. It's not very, very efficient in the case of large fires, and the presence of firemen is not an element we can count on in the minutes following eruption of the start of the fire, and that will be covered. So thanks for your attention. We are approaching 20 people, so it's less than first time.
Thank you, Stefan. So does anybody in the audience have any question? Something you would like to ask? No? Stefan, when we started with the task group 10 years ago, there was almost
That's 10
no...
years ago already, okay.
Yes, yes, almost more or less 10 years.
Mhm.
There was not too much people working on this. Do you see a growing interest on the professional community on this problem?
I would say that yes, and in there recently, you know what help? I mean, help, not help, but contribute to the aspect are fires of electric vehicles, which represents this open eye for the community, and it's for any type of structure. Bridges are also part of, but I think its interest is growing, and but the problem is, it's another type of, I mean, problems like collapse of bridges is any event contribute to the interest, the higher interest, but the problem is, the cost involved in. So if it's not mandatory, if it's not something we have to do, it's not always something people are open to consider. We have examples here in Montreal of important bridges where this kind of analysis was performed. Important bridges, so it's quite detailed with the impact. So I would say the answer is yes in the case of important bridges. In the case of and it is increasing, I would say. In the case of standard normal overpasses, etc., etc., the question is open. So I think from my perspective here in Montreal, maybe not so much. In Europe, I don't know. Perhaps you can add some explanation to this aspect.
So anybody in the audience would like to add something to this about the interest? No? Any question? Yes, we have one question, sorry. So Craig MacLeod, he's asking if you have looked at the use of polypropylene fibers in concrete mixes for mitigation. These were used on tunnel-type bridges in Windsor, Canada, on a new highway to allow moisture to travel through the concrete matrix when the fibers metal, supposedly helping to prevent explosive explosion due to rapid heating.
Wait, sorry. Yeah, we know that that's part of the
Melt.
food, the so-called design, and it's working, to some level. It's working, and of course, for the concrete structure, it's part of the solution could be used. The problem, however, is how to place this fiber, because they have to be concentrated in the part exposed to the fire. Mainly, so the mix should be carefully prepared, and the placement also as well.
Okay, thank you, Stefan. So anybody has any other question? No? So yes. So one from Gary, we should understand NFPA 502 language for bridge fire is quite limited and needs more discussion. What is your point on this, Stefan?
Could you repeat the question?
Yes.
I'm not sure I quite well understood.
Yes. Can you make like a critical assessment of what the NFPA is telling about bridges and fire? Do you think that it is appropriate? Do you think that it is not enough? That it is too broad, too general?
No, it's okay. I mean, from the it's general, of course, couldn't be approach otherwise, but you have the full recipe for the engineering analysis. So when you look at the engineering analysis as a tool, and you consider any in this analysis any aspect of performance, impact, etc., it's a good tool. But the problem is, and I will express here for my thought for following my long experience and life in three different countries, different types of codes, different approach, that basically we are teach to design structures. You are not necessarily teach to approach problem performance in the overall matter. So to see some like a life cycle performance, I referred in the presentation, or see how everything works before we even take the pen, the pen, and start to the computer these days, start to calculate, to design, and that's it very important, to make the step back and some kind of overall approach, the overall view of what we have in front of us in terms of structure, to make any detail considering the design fit in this overall picture. And that's not very easy. So from my perspective, the engineering analysis is quite interesting tools in terms of open line on this aspect, another aspect, another aspect. It put them everything under control. I don't want to tell attach some number to those. No, but to have them in the overall perspective, and from as far as fire risk are considered, see what's by the end of the process, where the energy and the in terms of construction money should be put to solve the problem or to lower the risk and to have an appropriate solution. Include and of course the client should be part of the of this process. That's very important.
Okay. And Gary, I would like to know your opinion about this. Hmm? Do you think that it is limited or not?
You asking me the question?
No, I'm asking to Gary, the engineer who made the question, if he wants to add something. Hmm? If not, we have another question by Craig. You mentioned intumescent paints, and you were not very happy with with their effectiveness for fireproofing in bridges. So do you think that they are more suitable for lower level hazards, such as steel bridges over a parking lot?
Yes and no. I mean, the paints are for use in buildings where the fire load is much lower than the case of bridges what can experience. But you refer to the storage, some use of the space under the bridge, but how to control? I mean, the problem is, to control the fire load underneath. And if it's low, if it's so like I don't shut off in the park could be considered, but even then I wouldn't put in the paint because it's loss of money. So the in general, the overall terms, I would say no. I mean, it was developed for buildings, and it performed very well in buildings. It's a very nice solution because it's not seen, and we have a lot of examples of airports, for large space, public for facilities. So bridges, no.
Okay. So does anybody in the audience have any other question? If not, Stefan, what I can do is that I can make a very short presentation about the case study of the bridge fire that we had in Valencia. What do you think?
Perfect. Use the time. Let
Okay,
us use the time we have.
so I will try to share my screen.
Mhm.
And I will tell you a little bit about a bridge fire that we had in Valencia. Let me see. Okay. So I don't know if you can see my screen. Somebody, Brinda, can you give me, or Firat, can you give me permission to share the screen? Or Stefan, can you stop sharing your screen, please?
I just stopped the sharing. Yeah.
Okay, so I will try now. 1 second. There it is. Okay, so now I need to find. Okay. Let me see. Okay, so this is a presentation that we put together with Juanjo Pagan, who is a fire engineer, and Antonio Spitale, who is a professor also here for Sapphire Day Sapphire. I don't know if you know, it is a software for structural fire engineering that was developed in Belgium. So we are going to Valencia. Oops, sorry, I missed the presentation. Sorry. Okay, Valencia is in Spain, in the Mediterranean Sea. This is the map of Valencia, and here you can see the old river bed, which is now a garden, and this garden is crossed by several bridges. One of them is El Puente de las Flores, Bridge of the Flowers, and it is called like this because it has plenty of flowers. As you can see there, some palm trees and so forth. And the structure is also quite original because you see it's not just pure longitudinal girders, there is a combination of longitudinal girders and diagonal girders. And these longitudinal girders, they don't go straight to the piers. There is a kind of displacement between the center of the pier and the longitudinal girders. So there are some elements here to hold the longitudinal girders and transfer the loads from the deck to the columns. Why this kind of strange or original arrangement for the girders? Because this is a very emblematic bridge for the city, and this is a kind of reminder of some old traditional floors, historic floors that you can find in some major buildings in the city. So this is the roof at the headquarters of the Valencian community government, and you can see this pattern of diagonal girders that it is copied in this bridge. It's a kind of remembrance. So you can see here a plan view with the longitudinal and the transversal girders. This is the cross section. This is a composite deck with concrete in the slab and then some boxes. And then there is a diaphragm girder which has the shape of an I section. And this one is on the abutments. It is here. So from time to time, they change the flowers, and the flowers come with pallets like those here. So they change the flowers, and then they store the pallets under the bridge. And this is what happened one day. One night in December 2022, somebody saw the pallets and set them on fire. And this is what remained from them. And this is how the area was after the fire. So you can see some spalling in the abutment. You can see some local buckling here, some small buckling also in the bottom flange, also in the web. And this is a detail. You can see the local buckling of the diaphragm girder, the supports, the elastomeric bearings. Well, in this case, they were pot bearings. They were completely burned. There were also some cracks in the weldings. And this is the expansion joint, and there was an upwards movement of the deck with respect to the abutment. So the bridge had to be closed for cars, so only pedestrians and bikes were allowed to cross the bridge. And then some in situ tests were performed. So in some parts, concrete cores were extracted to see if the concrete had been affected by the fire, the loss of the strength. Also, some samples were taken from the steel girders in order to check the resistance of these girders after the fire, also to check for the ductility. And then we were contacted by the town hall because at the beginning they thought about demolishing the bridge or the span that had been affected by the fire. But we said to them that if we invested some money on doing numerical investigations and some money in doing tests, maybe we would be able to save many elements of the bridge. So at the end, they decided that it was a good idea to perform this kind of analysis and to learn from the incident. So then the analysis is 3 steps. First of all, you need to do the fire model to obtain the heat fluxes that are affecting the structural elements. Then you do the thermal analysis to obtain the temperatures within the structural members. And then you do the structural model in order to see the structural response. Well, I will not enter into all the details of this, but basically we did a model with FDS and we were simulating the fire of the pallets, and we were checking, for example, that some flames were going outside from the deck because this is something that was observed during the real event. We could also see how the flames were spreading through time, and this was important because we saw some parts where there were no soot. So that meant that there was a big flame impinging here, and we could see this area matches the area with the flames here. So we couldn't do a very quantitative validation of the model, but we could do a qualitative validation of the fire model. Okay. Then we did, well, from here we obtained the adiabatic temperatures on the abutment and also on the girders, and then we perform with Sapphire the thermal analysis. I'm not entering into the details of this, but from the structural analysis, we could obtain the maximum expected temperatures in both the concrete and also in the steel girders. And in the steel girders, they were under 728 degrees, and this is an important limit because if you go beyond this limit and then you cool the steel very quickly, you can have a kind of change in the microstructure of the steel, and from being ductile, the steel can become fragile. So we were lucky with that because this temperature was not overpassed, so the steel ductility was not affected, and this was also verified by the tests that were done with the samples taken from the bridge. So this is a cross-section of the diaphragm girder, which was the most heated element. This is one of the diagonal, not longitudinal girders, and also the temperatures are very, very low, under 500 degrees. And the other one, this must be one of the transversal girders. Also, the temperatures are under 700 degrees. So we didn't go and never beyond this threshold of 728, 29 degrees, which is very important. And for the concrete, it was something similar. Even if we did not perform a detailed structural analysis, a cross-sectional analysis, but if we get a kind of qualitative idea using the 500 isotherm method from the code, you can see that the thickness of the concrete that was affected by the fire was very small, in the order of 1 or 2 centimeters, depending on the location. And the concrete slab was more than 26 centimeters of depth. So the concrete was just superficially affected. Then we did the structural analysis, and instead of doing an analysis of the full bridge, we took like a portion of the bridge. So you can see here the longitudinal girders, you can see here the diagonal girders. In green, those are the portions of the slab. Here we have the supports, and here we have the columns. And then we introduce some restrictions in order to take into account the influence of the rest of the structure. This structural model, we obtain the reactions at the supports without any fire, and we verify these reactions with the reactions given by a model done by a consultant who was working just at ambient temperature and had done an analysis with Sophistic. So the reactions of Sophistic matched more or less our reactions with Sapphire at ambient temperature, so we thought that the model was more or less well. Then we performed the analysis, and we saw that the bridge was able to sustain all the fire without collapsing. Although, to be honest, we saw some efforts that didn't make too much sense, like some elevation of some points here and there that were not observed in the real structure. So in order, this is important because this had to be done quickly because the bridge was closed. So we had a kind of immediate action to be taken, and that was let's try to repair the bridge, don't demolish that, and then with more time we refine our analysis. And in this refined analysis, we did a more complex model of just the diaphragm girder. I'm not entering into the details of this, but by doing all this detailed analysis, we were able also to capture the local buckling of the girder. So at the end, by numerical models, we were able to reproduce more or less what had happened during the fire event. And then regarding the repair works, finally, instead of demolishing the full segment of the bridge, there were some repairs on the abutment, like replacing all the concrete that had been damaged. Also, this portion of the diaphragm girder that had the local buckling had to be removed. So you can see, but instead of removing everything, it was just the lower portion of the girder was removed and a new one was placed there, and additional stiffness were placed also. This is for the elastomeric bearings, the pod supports. So they had to be changed. So the deck had to be lifted. And this is what you can see here. Those are the jacks that are lifting the deck. And in order to not introduce any web buckling in these elements, you see that some additional stiffness had to be placed. And all the process were closely monitored with LVDTs to measure the displacements, and also with strain sensors to measure unitary strains and the stresses in the structure. So this is, and then finally, since there were some things that we could not check numerically, we proposed to the owner, to the town hall, to do a load test and to compare the results from the load test, the deflections and the strains, with the values coming from a structural analysis, linear elastic structural analysis at ambient temperature. And everything worked very well. So finally, the bridge was back to service, and the town hall was happy, and the citizens also. So things that we have learned from this, that it's very important to try to preserve all the evidences after the event in order to collect information and to be able to perform the analysis. Also, that numerical models and experiments and load tests can help us a lot to take informed decisions and get substantial savings. And also, it was very nice that we had a redundant structure, so we didn't have just a single load path, but we had these diagonals that were able to transfer the load from one element to other. And also, if you compare the behavior of the box girder compared to the eye girder, this one is much better. So on this side, we were also lucky, because with eye girders, probably the damage would have been much higher. And also, well, this is already published in a journal. So if you want all the details, you can check them there. And this was possible thanks to the collaboration of the town hall, a contractor, and this is the company that did all the analysis at ambient temperature. So that's all. I think it was a good idea to show like an example of everything we have been talking about applied to a specific case. I don't know.
Yeah,
You have.
very interesting indeed. So that's another perspective. This fire, the action after the fire, very important.
Okay. So I don't know. You have any question? Anything, Gary? You said that it is difficult to participate in a discussion. I don't know, Brinda, you can allow Gary to talk. Yes, Gary, I think you can talk. Huh? I don't know if he's still here.
Hi, Gary. You're muted.
I'm unmuting and muting. So now I'm alive.
Okay.
Very good. So a very interesting presentation. One of the challenges we have in 502, and I'm one of the principal members on 502, is we really don't have enough expertise to have, I think, the informed discussion that we're having here. We really have a lot of experts about tunnels and not a lot of experts about bridges and other structures, so air ride structures, etc. So if you look at 502, you'll see a little less than a page about bridges and fire protection. And then you turn the document to the next page and you see 2 or 3 or 4 pages about tunnels and a lot more detail and a lot more prescriptive and helpful information. So for those who have not participated in 502, I'm going to offer an extended invitation to participate and at least sit in on the next set of meetings we're going to be having here. It'll be a few months yet. But you can easily put yourself in as a friend of the committee and you'll be informed of what's happening on the committee. And if you have any questions, I can help you get there. So very good presentations. I think other people might have wanted to talk as well, so I'll stop. Thank you very much.
Okay, thank you, Gary.
That's good.
So anybody else? Well, thank you so much for your attention, for your contribution. And we are open to your contributions to the group. And you are always very welcome to attend any of IABSE events. They are very nice. I always learn a lot and meet a lot of interesting people there. So hope to see you there. Wait. Okay. Okay, so I have one question. I will reply. They are asking if we model the springs in our model, in our structural model. Well, in the structural model, what we did is that we use non-linear springs. So the elastomeric bearings were working under compression, but not under tension. So this is what we did. Because these elastomeric bearings, they are not able to take tension forces. They can only take compression forces. Okay. Well, thank you so much. Thank you so much, Stefan, and all the participants, and hope to see you soon.
Thank you.
Thank you.
See
Bye.
you. Bye.